Hi everyone. Today we're going to be talking about how to graph square root transformation, which is going to be a blast, so get excited. So whenever we graph transformations, remember you guys, transformations are items that cause your graph to move around from our start function, which is called the parent function. So transformations might make it go left, right, up, down. It might make it flip upside down. It might stretch it vertically or compress it vertically. Okay, so whenever we graph transformations, we're always going to start from the parent function. That is always where we will start. So this graph is going to be your first graph every single time you graph a transformation. So I'm always going to be using these points. I'm not going to use the last point just because we don't really need the last point, but I'll always use the point 0, 0, 1, 1, 4, 2, and 9 and 3. And remember, the way that you get the y values, the reason why I picked these x values is because they are really easy to square root. Like, it's really easy to square root 0, 1, 4, 9. When you square root 0, you get 0. When you square root 1, you get 1. When you square root 4, you get 2. When you square root 9, you get 3. Okay, if I were to pick 2 as an x value, you can't square root of 2. Okay, the square root of 2 is like 1 point some. Okay, so I picked numbers for the x's that are easy to square root. So that is why I picked these for the x's. And then the y's, we're going to use our 0, 1, 2, and 3 because that's what you get after you square root the x's. Okay, so this will be the start graph every single time we graph a transformation. Okay, so in example 8 and 9, we're going to be not only identifying the transformations, which you guys are pros at because we did that in examples 1 through 3, we're also going to be graphing each transformation separately, which is awesome. The more transformations, the better. Something else we're going to be doing is at the very end, we're going to state the final domain and range for the final equation that we have graphed. All right, well, let's get going on example 8. Let's do it. Okay, so I have your equation right here. The first one we're going to be graphing, which, sorry, this should be example 8, not example 1. Sorry. Okay, so example 8 is the equation y equals 2 times the square root of x minus 3 plus 1. Okay, and remember you guys, we always start with the parent function, which I'm always going to use the values 0, 1, 4, and 9 because again, they're really easy to square root. And how you get your y values is by square rooting the x's. So the points we're going to be plotting are the points 0, 0, 1, 1, 4, 2, so 1, 2, 3, 4, 2. And the point 9, 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 3. So about right there. All right, so this graph, again, it's kind of like half of a parabola facing sideways. It's going to go like so. It's going to go like this. It's going to be like that. Okay, so remember, whenever you have a square root function, you always have a start point. Okay, so the graph's not going to keep going this way because if you remember, you can't have negative signs underneath the square root because if you have a negative sign underneath the square root, then you have an imaginary number. And we cannot see imaginary numbers graph on the real number coordinate system graph. Okay, so it will have a start point at 0, 0. Okay, so whenever we're doing transformations after we do the parent function, if you recall from when we did quadratic transformations, we always start with the a value. Now, it's not wrong if you don't do the a value first, it's just going to make your life a lot more complicated if you don't do the a value first. So I always like to deal with the a value first. After you tackle the a value, it doesn't matter if you do the h or k next. So again, I always like to do the a first just to make my life a little bit easier. All right, so what we're going to do is I'm going to add on to my parent function the a value. So my equation y equals 2 times the square root of x minus 3 plus 1, which one of these numbers right here is the a value? Well, the a value is the number right in front of the square root, which happens to be 2 in this case. Okay, so I'm going to add the a value onto my equation, which is a 2. Okay, and I'm just going to add it into the front. So each time we add on a transformation, I'm going to continue adding onto my equation. Okay, So remember, you guys can be math magicians. You can already predict what the graph is going to do before it even gets graphed, which is pretty exciting. Okay, so when the a value is 2, or when it's greater than 1 and not a fraction, I bet you guys remember what the graph does. Holy hot dog, you guys always know. So when a is larger than 1, that is when the graph will vertically stretch. Okay, so just imagine this graph is going to stretch upward, so it's going to kind of have a higher kind of arch as it goes up because it's going to be stretching up and away from the x-axis. Okay, so I already know what's going to happen. The graph is going to vertically stretch by a factor of 2. So that means the graph is going to be twice the height that it was originally. Okay, now all you have to do to get the points for the a value, just like when we did quadratic transformation, so hopefully this is a review. All I've done is I've copied down the parent function, which these are the points for the parent function. Okay, but the a value is going to go right in front of the square root of x. So this is like 2 times the square root of x. Okay, so these points are the points for the square root of x. Okay, so if this equation is 2 times the square root of x, what do you think I have to do to my y values to get 2 times the square root of x? You would just simply multiply all of your y values in the parent function by the a value, which happens to be 2 in this case. Okay, so all you have to do to get the points for the a value graph is you copy down the parent function points, and all you got to do is multiply the y's by the a. Okay, so 0 times 2 is 2. 1 times 2 is, oh, good golly, 0 times 2 is not 2. Demon Cat's got me, you guys. 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. And 3 times 2 is 6. All right, so my new points I'm going to be plotting for the a value graph are the points 0, 0, 0, 0, 1, 2, 4, 4, and 9, 6. Okay, and if we did it right, the graph should kind of stretch up vertically and kind of arch up more than it was originally. So I have the point 0, 0, the point 1, 2, the point 4, 4, so 1, 2, 3, 4, and then 1, 2, 3, 4. Sorry, 1, 2, 1, 2, 3, 4, and then over 4, so like right here. All right, and then the point 9, and then 6. So we're going to go 1, 2, 3, 4, 5, 6. So about right here. Again, if you have graph paper, you guys will be a lot more accurate. So I always encourage you using actual graph paper when you do this. Whoa, look at this, you guys. See how it's kind of arching upward more because it vertically stretched away from the x-axis. Look at that. All right, now, after that, it doesn't matter if you tackle the h or k value first. I personally like to do the h first, but if you do this problem and you do the k value first, then the h, your final graph will look the same as mine. Now, your middle graph won't look the same, but your final product will be the same, which is what matters. Okay, so again, it doesn't matter which one you do first. I'm going to do the h value first, and for the h and the k value, you don't have to make a table. What we're going to be doing is counting on our graph to get those points. Okay, so what I'm going to do, I'm going to take my most recent equation, which is this one, y equals 2 root x. And then I'm going to add on the h value. Which one of these values in my equation is the h value? Would it be the 2, the 3, or the 1? Well, the h is whatever's added or subtracted to the x. So the number that's added or subtracted to the x is the 3. Okay, so in my equation, I'm just going to simply add my h value onto my most recent equation, which is this one. So I'm going to add on the x minus 3. And remember, you guys, you can already predict what's going to happen on your graph before you even graph it, which is really awesome. Okay, so do you remember when you have x minus 3 as your h value, what will your graph do? Well, don't forget with the h value, you have to think the opposite. And remember, h, we think horizontal, so it's going left and right. Okay, so if we think the opposite with the h value, I know since we're minus 3, we're tempted to say left because that is a negative direction. Okay, but we think the opposite. So when we see a -3, we're actually going to go right. Okay, so we know the graph is going to move right. I'm actually going to write moves right. All right, moves right 3 spaces. Okay, so what I'm going to do on my graph, I'm going to start from my most recent graph, which one of these graphs is the one that I did most recently? Absolutely, you guys, it would be the pink graph. So I'm going to start from the pink graph, and I'm going to count all of my points 3 spaces to the right. Okay, so I'm going to start from here. I'm going to count 3 to the right, so 1, 2, 3. All right, I'm going to start from here and count 3 to the right, so 1, 2, 3. About right here. Let's see here. 1, 2, 3. Yep, right there. All right, and I'm going to count here. So 1, 2, 3. About right there. And I'm going to count this one. So 1, 2, 3. All right, so here is the pink graph moved to the right 3 spaces. Cool, right? Okay, and then my final graph is going to be the k-value. Okay, so I'm going to add on the k-value to my most recent equation, which is this one. So we have y equals 2 times the square root of x minus 3. Now, which one of these values is the k-value? The 2, the 3, or the 1? What do you guys think? Well, the k-value is the number that's added or subtracted on the very end of the equation. So that would be the 1. So I'm going to add 1 onto the end of my equation. All right, and we can already know what the graph is going to do. So let's go ahead and state the transformation. Okay, so remember the k-value, we think kangaroo, which kangaroos go up and down if you have a normal kangaroo. All right, so if we go up or down, okay, with the k-value, you don't think the opposite. So the positive direction if you're going up and down is to go up. Okay, so I already know my graph is going to move up 1 space. All right, and all I'm going to do on my graph, I'm going to start from my most recent graph, which my most recent graph is the orange graph. Okay, so I'm going to start from my orange graph, and I'm simply going to move all of my points up 1 space. And then I'll have the graph for the equation y equals 2 times the square root of x minus 3 plus 1. All right, so I'm going to move up 1, so up 1 right there. I'm going to count up 1. All right, from this point, I'm going to count up 1, so right there about. And I'm going to count up 1. I guess this was 1 as well. It's right there. And I'm going to count up 1. Look at that beautiful graph. I always love graphing transformations. They make like a beautiful piece of artwork right here. All right, so the blue graph is the final graph that would graph this equation right here. Okay, so the last thing we're going to do is to find the domain and range. But before that, don't forget your graph deserves a name. Make sure you guys name your graph, which I'm going to name my graph Gregory. I think that's a great name for my graph. Okay, so now we're going to find the domain and range of only your final graph. Okay, which looking at this graph, there's kind of a lot going on. So I'm going to draw the graph separately so I can see it. And it's only going to be like a rough sketch, you guys. All right, so I see that my start point is at the point 3, 1. All right, so 3, 1 is my start graph. And then the graph kind of does something like this. Again, it's a rough sketch, but that's okay. All right, I need to make sure I add the name. It deserves a name, you guys. Okay, so the domain and range, you can find the domain and range doing what we normally do. So remember, domain, you ask yourself, how far left and how far right does the graph go? Which if you see here, the furthest left the graph goes, so this is the point 3, 1. The furthest left on the x-axis that it will go is 3. And then how right does it go? Well, how far right it goes? Well, this arrow means it's going to continue to infinity and beyond with Buzz Lightyear for forever in the positive x direction. Okay, so these values over here are things like 4, 5, 6, 7. Are these numbers larger or smaller than 3? Well, they are larger. So for my domain, I could say my x's are all going to be greater than or equal to 3. Greater than or equal to 3. Okay, and I know that it's equal to because I actually have a point there. Okay, so there's a point there, which means it equals that point. Okay, now, The other way you can find the domain. So if you don't like looking at the graph, I have like an algebraic way. If you like to solve things instead of looking at the graph, the algebraic way, if you're looking here at your equation, the way that you can also find the domain is by using what is inside of the square root. So I'm going to use x minus 3. All right, now we know that all values inside the square root have to be greater than 0 because what happens when you have a negative sign underneath your square root? Well, that would make it an imaginary number. And remember, we can't see imaginary numbers on the real number system graph. Okay, so we know that all the values inside the square root have to be greater than or equal to 0 because all numbers that are greater than or equal to 0 are non-negative. Okay, so what you can do, another way to find the domain, you can simply set whatever's inside of your square root to be greater than or equal to 0 and solve for x. So if I solve this inequality for x, if I add 3 on both sides of the equation, negative 3 plus 3 will cancel and turn to 0. 0 plus 3 is 3. So if you see, you get the same thing if you solve it that way. So the algebraic way to find the domain, you set whatever's inside your square root, which is the x minus h, and you set it equal to 0. So if you prefer to solve algebraically, that is the way to do it. All right, and then for our range, that's the y values on the graph. So that is how high and how low your graph is going. So you ask yourself, how low does the graph go? So my lowest y value on the graph, if you see here, is the 1. And then you say, well, how high does the graph go? Well, this graph, it doesn't really look like it, but it does steadily get higher and higher. It's going to keep increasing. So it's going to head to infinity and beyond with Buzz Lightyear. It's going to keep heading upward for forever. So these values up here are things like 2, 3, 4. Okay, are those numbers larger or smaller than 1? Well, they are larger than 1. So for our range, we're going to say y is greater than or equal to 1. And remember, we can say it's equal to because we actually have a point at 1. Okay, now again, there's also an algebraic way to find the range if you don't like looking at the graph. So if you guys notice, which value is a 1 in your square root equation? Do you guys see that the k value is a 1? Okay, so if your graph is increasing, you can simply say the range. So if the graph is increasing, you can say, so if it's headed upward, okay, you can simply say the range is y is greater than or equal to the k value. So my k value is 1, my graph is increasing, so I can say y is greater than or equal to 1. Now, if the graph was decreasing, so headed downward, so when it's decreasing, okay, let's say this graph was heading downward, like that. All right, so these numbers here larger or smaller than 1? So these are things like 0, -1, -2. Well, they are less than 1. They are smaller than 1. Okay, so when the graph is decreasing, we're going to say y is less than or equal to the k value. Okay, so this is the shortcut if you like an algebraic way to find the range instead of looking at the graph. Well, there you go, you guys. You guys have graphed all the transformations for your square root function, and we have found the domain and range. Example 9 is going to be just as fun, so get excited.